In Unit 1, we have already learned the underlying concepts of kinematics. We learned motion along straight line, and motion in two dimensions such as projectile motion and circular motion. So far, we have discussed only uniform circular motion, and we do not consider a rotating body with acceleration. In this unit, we are going to discuss circular motion in more detail. We will discuss the following important quantities of rotational motion, such as angular position, arc length, radius, angular displacement, time interval, average angular speed, instantaneous angular speed, average angular acceleration and instantaneous acceleration. Good luck. Now, let us begin our discussion with angular position. In Unit 1, we had described the position of a body in terms of its x and y coordinates, relative to some point of origin. In rotational motion, we can describe the position of a particle p on a rigid body in terms of called angular position. To explain this, imagine a circular disk, wherein a particle p is located at a distance or radius r, from the center of the disk, O. The location of this particle can be described in terms of angular position, and is denoted by theta. The angular position of the particle is the standard angle measured counterclockwise from the reference line positive x-axis. It is usually measured in degrees. As shown, the particle p has an angular position of 30 degrees. In this figure, the angular position of particle b on the disk is 270 degrees. Take note that the angular position is always measured counterclockwise from positive x-axis. When the particle c is at the reference line, then the angular position is theta is 0 degree. Angular position can be expressed also in other units of angle, such as radian and revolution. From geometry, the following conversion factor can be used. 360 degrees is equal to 2 pi radians, and these are equivalent to 1 revolution. Later, we shall see that the unit radian is the standard unit of angular position that can be used in understanding the relationship between rotational motion and translational motion. Now, let us investigate what happens to the position of a particle p, as the disk rotates at a fixed axis perpendicular to the plane of the disk, and passing through the center of the disk. As the disk rotates counterclockwise, the angular position of the particle p has changed from its initial angular position theta sub I, to a final angular position theta sub f. This progressive change in angular position of the particle is called angular displacement, and is denoted by delta theta. Mathematically, angular displacement is given by the equation, final angular position, theta f, minus the initial angular position, theta sub I. The SI unit of angular position is also radians for as long as the initial and angular positions are expressed in radians. Depending on the state or direction of the rotation of a body, angular displacement can be a positive or negative value. It can also be zero. When the body is rotating counterclockwise, the angular displacement is a positive value, since the final angular position is greater than the initial angular position. If the body rotates in opposite direction or in clockwise direction, the particle's angular displacement is a negative value, since the final angular position is less than the initial angular position. When the body is not rotating, obviously the angular position of a particle on the body is zero. The angular displacement of a particle p corresponds to an arc length, denoted by letter d. It is a distance traveled by the particle as it moves along arc subtended by the angular displacement expressed in radians. Mathematically, it is computed as the product of angular displacement, delta theta, and radius r. Take note when using this formula, the angular displacement should be in radians. Always convert it in radians, if it is expressed in either degree or revolution. Its unit depends on the unit of the radius. If the radius is in meter, then the arc length is also expressed in meter. Arc length is important when dealing with a circular body rolls along a flat surface. A rolling body consists of two simultaneous types of motion, rotational and translational motion. Imagine a point P on the rim with radius r, which has an initial angular position of 180 degrees. If the body rotates counterclockwise, it also rolls, until point P touches the flat surface. As the body rotates, it also travels along the straight line equal to the amount of this arc length. The wheels of the car or the bicycle are some example of rolling bodies. The arc length produced by the motion of the particle on the rim of the wheel is equal to the distance traveled by the body along the flat surface. If the wheel rotates 360 degrees, it actually translated with a distance equal to the circumference of the rim of the wheel, 2 pi r. This concept shows how the rotational motion is related to the translational motion of a rolling body. Later, we shall A rotating body moves at different rates, and to determine how fast a body rotates, we need to determine its angular speed. It is defined as the rate of change of the angular position of a particle on a rotating body. Here we are going to discuss average angular speed and instantaneous angular speed. Average angular speed, denoted by the Greek alphabet omega sub ave, of a rotating rigid object is the ratio of the angular displacement, delta theta, to the time interval delta t. Imagine a point P, which has an initial angular position of 50 degrees at an initial time 0. If the disk rotates counterclockwise, its angular position changes to 150 degrees 1 second later. We see that, at 1 second time interval, the point has been displaced by 100 degrees. So it means that, using the formula angular displacement divided by the time interval, the disk has an average angular speed of 100 degrees per second, and it is equivalent to 1.75 radians per second or 17 revolutions per minute. Take note that the SI unit of angular speed is radian per second. Other customary units can also be used, such as revolution per second, RPS, and revolution per minute, RPM. RPM is much easier to visualize than radian per second. RPM is the number of turns of a rotating body in 1 minute. It is commonly used in indicating the speed of rotating machines, such as motors, generators and turbine. The motor used in electric fan rotates at an average speed of around 1,725 revolutions per minute. A typical steam turbine operating in power generation industries can rotate at 1,800 to 3,600 revolutions per minute. If we treat angular speed as a vector quantity, its value can be positive or negative depending on the direction of rotation of the body. Angular speed is positive when the body rotates counterclockwise and negative when rotating clockwise. In Unit 1, we have discussed the instantaneous velocity of a body. In rotational motion, we can also describe the rate of movement of a rotating body at any point in time by considering instantaneous angular speed. It is defined as the limit of the average speed as the time interval approaches 0. It is also expressed as the first derivative of angular position with respect to time. Now it's time for sample problems. Problem number 1. The particle P on a 10 cm diameter disk is located at 3 cm from the center. The disk rotates at an angular displacement of 60 degrees in 0.02 second. Letter A. What is the arc length traveled by point P at this time interval? Letter B. What is the average angular speed of the disk in radian per second and revolutions per minute? Letter C. What is the arc length traveled of point A on the rim of the disk? Let us list down all given information. The diameter of the disk is 10 cm or 0.1 meter. The distance of point P from the center R is 3 cm or 0.03 meter. We have also angular displacement of 60 degrees, in a time interval of 0.02 second. What we are looking for is, letter A, the arc length of point P, denoted by letter D. Letter B, the average angular speed, and the arc length of the point at the rim, D sub rim. Now, let us solve for letter A. The arc length of point P is simply, we multiply the angular displacement with the distance r. Make sure we convert 60 degrees to radian, using the conversion factor 2 pi radian, over 360 degrees, before multiplying with 0.03 meter. So the arc length D is 0.031 meter. Now for letter B, we solve for average angular speed. Average angular speed is equal to the angular displacement divided by the time interval. Substituting the given information, the average angular speed of the disk is 52.36 radians per second. Then in order to convert this to RPM, we multiply this with the conversion factors. 1 revolution is to 2 pi radians, and 60 seconds is to 1 minute. So the disk moves at 500 revolutions per minute. Lastly, for letter C, to solve for the arc length of the point and the rim, we first solve of the radius, that is half of the diameter, which is equal to 0.05 meter. Take note that the angular displacement of any particle on a rigid body is constant, therefore the angular displacement of point A is also 60 degrees. Then again, converting this to radians and multiplying by the radius 0.05 meter will give an arc length of 0.052 meter. Are you ready for problem number 2? Okay, let's keep up. Problem number 2. The angular position, in radians, as a function of time t, in seconds, of a particle p, on a rotating pulley is given by the expression, theta equals 2t squared, plus 1.5 of t, minus 2.5. Letter A, what is the angular displacement of the particle during the time interval 1 to 5 seconds? Letter B, determine the average angular speed of the pulley at this time interval. Letter C, what is the instantaneous angular speed of the pulley at time 2 seconds and 3 seconds? Now, let us establish the given information. We have given the angular position equation, theta, which is equal to 2t squared, plus 1.5 of t, minus 2.5. For letter A and B, we have initial time and final time of 1 second and 5 seconds, respectively. And for letter C, we have time, 2 seconds and 3 seconds. Then we list down required quantities. Letter A, the angular displacement. Letter B, the average angular speed, and for letter C, the instantaneous angular speed of the pulley, 2 seconds and 3 seconds later. Alright, we are now set. For letter A, to solve for the angular displacement, we need to solve first for the initial and final positions of the point on the pulley, between time interval 1 second and 5 seconds, by using the angular position equation. Substituting 1 second to time t, will give a position of 1 radian. Then for a time of 5 seconds, the position is 55 radians. Then, we simply subtract the initial position from the final position, therefore the angular displacement during this time interval is 54 radians. Can you still follow? Next is letter B, the average angular speed is equal to the angular displacement, 55 minus 2 radians, divided by the time interval, 5 minus 1 second. So the answer is 13.5 radians per second. Then lastly, for letter C, for instantaneous angular speed at 2 seconds and 3 seconds. To answer this, you should derive the angular speed equation by getting the first derivative of the angular position equation, 2t squared, plus 1.5t, minus 2.5. So its first derivative is 4t plus 1.5. Then, we are now ready to solve for the instantaneous angular speed at time 2 seconds. We simply substitute the time t with 2, then pressing on your calculator, so the angular speed at 2 seconds is 9.5 radian per second. Then at 3 seconds, we again substitute the time 3 seconds, it gives 13.5 radians per second. Remember, for as long as we know the angular equation, we can always determine the numerical value of the instantaneous angular speed, at any point in time. Now, let us check what have you learned. Exercise number 1. A bicycle wheel of diameter 622 mm, rotates clockwise at an average speed of 15 radians per second. Letter A. What is the angular displacement, in radians, of the particle on the rim of the wheel for a time interval of 10 seconds? Letter B. How far the bicycle has traveled in this time interval? Letter C. Through how many complete revolutions does the wheel rotate? When you turn on your electric fan, the fan blade started to speed up. Then when you decided to turn it off, it will begin to slow down and eventually stops. It means that the angular speed of the fan is changing. This rate of change of angular speed is called angular acceleration, denoted by the Greek alphabet, alpha. Here we are going to discuss average angular acceleration and instantaneous angular acceleration. Let us begin with the average acceleration. The average angular acceleration of a rotating rigid body is the ratio of the change in angular speed, delta omega, to the time interval, delta t, wherein the change in angular speed is the difference between the final angular speed and initial angular speed. The SI unit of angular acceleration is radians per second squared, for as long as the unit of the initial and final angular speeds is radian per second, and the time interval is in seconds. The figure below shows two disks rotating counterclockwise, one is speeding up and the other is slowing down at a certain time interval. Since both disks rotates counterclockwise, their initial angular speeds, omega sub I, are positive values. When the disk speeds up, its final angular speed is greater than the initial angular speed, therefore the average angular acceleration of the disk is a positive value. On the other hand, if the disk is slowing down, its final angular speed is less than the initial angular speed, therefore the average Take note that a positive value of acceleration does not necessarily mean that the rotating body is speeding up, and a negative value is slowing down. How about if the body is rotating in clockwise direction? As you can see in the figure below, when the disk speeds up, its angular acceleration is a negative value, while a slowing disk has a positive value of angular acceleration. Now, to generalize these, always remember the following. Number 1, when the initial angular speed and angular acceleration are in the same direction, both positive or both negative, the rotating body speeds up. Number 2, when the initial angular speed and angular acceleration are in opposite direction, one is negative and the other is positive, the rotating body slows down. In Unit 1, we have also discussed instantaneous acceleration of a body. In rotational motion, we can also describe the acceleration of a body at any point in time by a concept called instantaneous angular acceleration, denoted by the Greek alphabet alpha. It is the limit of the average acceleration as the time interval approaches zero. It is also expressed as the first derivative of angular speed, or the second derivative of angular position, with respect to time. Now let us give an example of angular acceleration. Problem number 3. A disk is initially rotating counterclockwise 100 revolutions per minute, decelerates at an average of 5 radians per second squared for 0.5 second. What is the angular speed, in RPM, of the disk after this time interval? Establishing the given information. As mentioned in the problem, the initial angular velocity, omega sub I, is positive 100 revolutions per minute. This is a positive value since according to problem, it is rotating counterclockwise. Then, the problem stated that the disk decelerates, so we have negative acceleration of 5 radians per second squared, for a time interval of 0.5 seconds. We are asked to solve the final angular speed, omega sub f, 0.5 seconds later. And we will express our answer in RPM. The first thing we need to do is we need to convert the initial velocity in terms of radians per second. To do that, we multiply it with the conversion factors 2 pi radians per 1 revolution, in 1 minute and 60 seconds. Pressing on the calculator will give 10.47 radians per second. Then, from the formula of average acceleration, final angular velocity minus the initial angular velocity over the time interval, we solve for the final angular position. A little bit of algebra will give, final angular velocity is equal to the initial angular velocity plus the product of angular acceleration multiplied by time interval. Then substituting the given information, will give a final angular velocity of 7.97 radians per second. This is not the final answer yet, since we are going to express this in terms of RPM. So we multiply this by the conversion factors 1 revolution is to 2 pi radian, and 60 seconds in 1 minute, therefore the answer is 76.13 revolutions per minute. From this result, we see that 0.5 seconds later, the disk really slows down from 100 revolutions per minute to 76.13 revolutions per minute. Can you tell the time when the disk comes to rest? Now it's your turn, let us check what have you learned. Exercise number 2. A portable spin dryer rotates initially at a high speed of 3,200 revolutions per minute. After the drying operation, it started to slow down at a rate of 5 radians per second squared. How many more minutes the dryer rotates?